Naming molecules is about as easy as naming a child, which is to say, very difficult. But why are there so many rules to naming chemicals? The answer is very practical. It's for clarity. The goal of these rules is to create a two-way street to transform molecular structure into name, and vice versa. But the outcome of clarity and consistency came at the cost of complex naming conventions. By covering some common molecular patterns, I hope to provide some familiarity with the naming conventions of ionic molecules and some simple covalent molecules. Bonds, bonds, bonds. Atoms share electrons when bonding, but if one element pulls on electrons more than the other, the class of bond change. The pull of an element on an electron is measured on the electronegativity scale. Equal atomic pull means nonpolar covalent, favored pull makes polar covalent bonds, while full-on electron transfer gives bonds ionic character. A simple way to tell which category a bond falls under is by looking for metals. Metals cover most of the periodic table, with nonmetals mostly residing on the right side and blue over here. There are a few metalloids in the middle acting in transition between metals and nonmetals. That's it. Metals, nonmetals, and metalloids. A quick rule of thumb is that a bond between a nonmetal and a metal is usually ionic, while bonds without metals are almost always covalent. So, to get started, we're going to have to get to know a few common polyatomic ions. In case you don't have it memorized, it's alright. I've got a handy-dandy little list for you right here. These ions are in everything. Some recognizable examples are the ingredients in science fair volcanoes. Both vinegar and baking soda have polyatomic ions in them. An extra special one is this here ammonium, which is the only polyatomic ion besides hydronium that has a positive charge. A neat little trick to remember whole groups of them at a time is to pay attention to the prefixes and suffixes. Looking at this corner are ions that involve chlorine and oxygen. Each root signals the relative amount of oxygen. Perchlorate has one extra oxygen relative to chlorate, chlorite has one less, and hypochlorite has two whole less oxygen relative to the chlorate ion. Thing is, every polyatomic ion in Stanley has the same charge. This holds true for nitrate, sulfate, and phosphate groups as well. One last little note are the suffixes ik and us. Some transition metals have multiple oxidation states, and these suffixes signal which one the ion is currently in. For example, the cupric copper ion shares one more electron than the cuprous copper ion. Ik is more giving than us. Finally, we actually get to start naming molecules now. For ionic compounds, find out which element is the metal and say that one's name first. Then say the name of the nonmetal with the suffix "ide" at the end. Simple table salt is made out of the metal, sodium, and the nonmetal, chlorine. So when ionically bonded, the molecule is known as sodium chloride. If the metal has multiple oxidation states, you have to specify how many electrons are being shared with Roman numerals. When two irons meet three oxygens that form rust, it is known as iron 3 oxide. With polyatomic ions in the place of the nonmetal, you don't even need to add the "ide" at the end. Just say the name of the metal and the ion. In that order, and you're set. An example of this is the common rock calcite, also known as calcium carbonate. It's found in limestone and antacid tablets. Now, if you want to go in the opposite direction, from name back into chemical formula, you have to do some balancing of charges. The charges of the positive ion, known as the cation, and the negative ion, known as the anion, should be the same. Find the ratio of each ion that balances each other out, and that is the chemical formula. Now, before we get to naming covalent bonds, I gotta make sure we know our numbering prefixes. The most common ones are the first four, but I'll cover the first 10 just in case. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. One more time. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Here are some examples. Tetra, as in tetrapod, the superclass consisting of all four-legged animals, from birds to dinosaurs to mammals. Tri, as in tricycle. I'm sure you can figure that one out on your own. Di, as in dialogue, a conversation between two people. And as of a few hours ago, monarch, as in King Charles III. Moving on. Naming covalent molecules can get to be pretty complicated. Looking at you, organic chemistry. So to keep things simple, I'm going to stick with only binary covalent compounds. These are compounds with two different elements. Name these molecules by stating each element's name with a prefix showing how many there are. But the second element needs an "ide" at the end. But how do we know which element comes first? It all comes down to electronegativity. The element with lower electronegativity is named first. Generally, if the element is further left on the periodic table, then it has lower electronegativity. But if they're in the same column, the element further down on the periodic table has lower electronegativity. Put simply, the element that is further left and down is listed first. One more thing to remember, if the first element is singular, it does not need a prefix. An example of a binary covalent compound is carbon monoxide. One tricky situation with naming is the case of diatomic elements. These are elements that form bonds pairing with themselves at standard temperature and pressure. These guys are kind of weird because they're commonly referred to simply by their elemental name with no changes. When somebody says oxygen gas, it almost always means oxygen in its diatomic form, which can be kind of confusing because every other element's name refers to its unbonded singular form. Good thing is, they're easy to remember if you have a periodic table in front of you. There are 7 of them, and they form a shape of a 7 with these 6 elements, and hydrogen is the last diatomic element. And the last class of molecules I want to talk about are the alkanes. Alkanes are important for organic chemistry because they form a backbone using elements universally used in organic bonds, carbon and hydrogen. Carbon chains are named based on the number of carbons in that chain. A 1-carbon chain uses the base meth, 2 carbon chains uses the base eth, 3 prop, 4 bute, 5 pent, 6 hex, 7 hept, 8 oct, 9 non, and 10 dec. Hydrogen-saturated chains without double or triple bonds are called alkanes. They're usually colorless, odorless, and burn cleanly in combustion reactions. Longer alkane chains tend to have higher energy density and boiling points, which makes them useful in different applications. The most recognizable alkanes are probably methane, a potent greenhouse gas, propane, a portable stove fuel, and octane, the alkane that defines the rating system seen on gas pumps. Now, to put all of that learning to use, I've got some practice questions set up. Number 1, chemical rust is written as Fe2O3. Which is the correct name for rust? Pause if you want to solve these before I give away the answer. Now, this is a little bit of a debate because both answers C and D are correct. The other answers are close, but they either mess with the bond type or the oxidation number of iron. Iron 3 oxide is the exact same as ferric oxide, but it'd be kind of hard to get it if you didn't already know the oxidation states of iron, so I put both answers in. Next question. How many ammonium ions does it take to balance out a single phosphate ion? Pause. Pause. The answer is C. Ammonium has a +1 charge and phosphate has a -3 charge. Great job, kiddo! Now, just 2 more questions and we're done with this thing. Which is the correct name for water, or H2O? Is it dihydrogen monoxide, hydrogen monoxide, hydrogen oxide, or oxygen dihydride? 3, 2, 1. Answer is A. When bonding 2 nonmetals, both elements need to specify the prefix. Also, hydrogen has a lower electronegativity than oxygen, so it's listed first. Last one now. Which is the correct name for a 7-carbon alkane? Heptol, heptane, septol, or septane? The correct answer is B, heptane. I added in the Latin root for 7 instead of the Greek one. Let's mix up. Thanks for listening in. If there's one thing you want to remember, it's that the mitochondria is the powerhouse of the cell.